Hello, good evening. Am I audible?
Good evening. Yes,
Yeah.
you are on.
Okay. Okay. So today is the second revision session. In the first, I think we have almost covered till basis, right?
I have a query regarding the same.
Go ahead.
There is an R3 which was taught, and there is a condition given x plus y is equal to 0.
Okay.
I'm getting confusion. How are we getting two independent variables? Whenever they should be just one independent variables, right? Because we are getting two bases in that.
Uh, what is your, set?
R3, x comma y comma z.
And what is the condition?
X plus y is equal to 0.
X plus y equal to 0. Yeah. So what are the independent variables you are thinking here?
Only z.
Is it?
Because we take any arbitrary vector like 1 comma minus 1 comma 0, 2 comma minus 2 comma say 60, and 3 comma minus 3 comma
Okay.
80.
Okay.
Okay.
So this is your. Can you see my screen?
Yes, sir.
Okay. So this is the set you are talking about, right?
Yes, sir.
This is the set. Yeah. Okay. So what does it mean? So I can write it like this also. Right? So x equal to your minus y, correct?
Yes, sir.
So can I write it like this?
Yes, sir.
So how many variables this set depends on?
1.
Is it
Oh, sorry. 2.
Two.
two
Two
variables, right?
variables.
So is it clear now why this depends on two variables?
Yes, sir. But when we take, say, arbitrary vectors based on this condition, we get rank is equal to 2, like minus 1, 1 comma
That is different. Rank is equal to 2 means, suppose you take one vector. Give me an example.
1 comma minus 1 comma 60.
Okay.
2 comma
Says,
minus 2 comma 2 comma say 10.
so you are giving different examples, right? Which are in the set.
Three
Huh.
vectors I'm taking. Yeah.
Why you are taking three vector?
Because it's in R3, right?
So I think you are confused with whole the rank and dimension thing. Have you attended any live session before?
No, I've attended a lot,
But you are right. You
So
said rank is two.
what rank of a matrix means and what dimension of a vector space means? Can you tell me what is the difference between these
rank
two?
is equal to number of dependent variables and
Is it? No, rank of a matrix I am asking.
okay, that is equal to m by n, right? So I mean,
Is it?
if it's an m into n, then rank will be n, right? Uh, so,
Not really. I mean, what is the rank of this matrix? Say, what is the rank of this matrix?
3, right?
3.
We have to calculate
Two.
that.
Rank is 2. Yeah. So, I mean, what is rank basically? What do you understand by rank?
The number of pivot ones, I mean, there are 3 pivots in this, so it will be the rank will be 3, right? Number of dependent variables.
What are the variables here in the matrix? Is there
Right?
any variable in the matrix?
Uh, Not really.
So, and okay, so I will come back. What is the dimension of, suppose I am giving you the whole R3 space. What is the dimension of R3?
3.
Okay. Now, suppose I am talking about only XY plane in R3. What is its dimension?
2.
Okay. Now, how we are calculating this dimension?
I
I
mean,
mean, what is the meaning of the dimension?
I mean, say we have a room and the wall will be R2, so that's the dimension in R3, right?
But why that wall is of dimension 2?
Because the third dimension is 0.
Mm, it may not be, right?
I mean, that's
Suppose,
constant. That's constant. Sorry.
some constant. I mean, that is not independent, basically, right?
Right, sir.
Yeah. So there is a difference between dimension and rank of a matrix. So can someone tell that what is the rank of a matrix? Anyone?
Sir, the rank of the matrix is the number of non-zero rows, sir. If there is a non-zero row, then it's then we can say, let's suppose if
So what is rank of
uh,
this matrix?
sir, two, sir.
Two.
After
But there is no non-zero
Or
row, right?
yes, sir.
Because
no,
we
sir,
use
if we
a
solve now,
row echelon
if
form.
we solve, we get the
In
two
the row
non-zero
echelon,
row.
One by one, one by one.
By converting a matrix in a row echelon form, if
Hmm.
there is a uh, there is a number of non-zero rows will be equal to the rank of the matrix.
Okay. So suppose I am trying to convert in Roaston form, what I will get. So this is 0, 1, 1, right? R3 minus R1. And then again, if I do this R3 minus R2, I will get the last row to be 0. Okay.
Yeah, rank is 2.
So this is in Roaston form, or rather reduced Roaston form. So the rank is, so there are two non-zero rows. So rank is 2, rank of this matrix.
Yeah.
Suppose this is A, rank of A is 2. Now what does that mean? Suppose I am taking these 3 rows as my vector. What does it imply?
They are making a they are dependent variable.
two
Dependent
linearly independent variables. They are
linearly
not minimally
Suppose I
independent.
am taking these 3 vector.
Yeah.
Okay.
Yeah.
So, and I am taking the span of these 3 vector. Now, this is a vector space, right? Span of some set,
Okay.
correct?
Yeah.
Why span of some set is a vector space? Why span of some set is a vector space? I mean, what is the definition of span of some set?
Sir, the definition of
Hmm.
the spanning set is the if we combine or if we multiply some constant, we get the another vector, sir. For example, if we said the here the vector 101 and the vector 2011, if we
Hmm.
add this vector, we get the vector 3, sir. And the determinant of the spanning set is sir 0.
Okay. Determinant of spanning set does not make any sense. Basically, if you write this in a matrix form, then the determinant of that matrix is 0. That is correct.
Sir, with
Yeah,
the help of these three vectors, I can write any element of that vector space.
exactly. So vector span of this set means basically, suppose I am taking 3 or more than 3, doesn't matter. Suppose n vectors. So span of this thing is basically set of all combinations, right?
Yeah.
All such combinations. Vi is in this set. This set is S. So
Which will qualify the rule of vector space.
yeah, basically we are taking all such linear combinations,
Yeah.
right? And that whatever the space we are getting, that is basically forms a vector space, right?
Yeah.
Now suppose I am taking these 3 vectors which I have started with and which are rows of this matrix whose rank is 2. Now what does that mean? That means suppose I am taking this. So this V is spanned by these 3 vectors that we know, right? The spanning set of this vector space contains 3 vector space. Now is this set, these 3 vectors, are they linearly independent?
No, sir.
No,
No.
no.
Because I
No,
can
sir.
write
One of the vector.
this combination. Yeah, exactly. One of the vector in terms of the other two. Correct? So I can write this equation, right?
Yes.
So I can write a non-zero combination of these three vectors, which is giving me the zero vector. Right? That was the definition of linear dependency.
Yes.
So these three vectors are linearly dependent. Now, if we eliminate this 1, 1, 2 from this set, suppose I am eliminating this. So basically, what does it mean? 1, 1, 2 can be written as some linear combination of these two vectors. So if we only consider this set, right?
Yeah.
So now is this set linearly independent?
Yes, sir.
Yes.
Yes, this is also linearly independent. And is this set spans the original vector space which we have started
Yes.
with?
Yes.
Yes, because even 1, 1, 2, which was inside the set, that itself is a linear combination of these two vectors, right? So whatever the vector will come as a combination of this, that will also be written as a combination of this and this. Okay.
Okay,
So
scroll a
these
bit
two
up, sir.
vector only.
Just
Yeah.
for one. Can you scroll a bit, sir? I just wanted to see the. Just for a minute.
Okay.
Scroll up.
Yeah.
Top, little bit more, little bit more. I want to see the matrix. No, still further before the echelon. Oh, 1, 0, 1, 0, 1, 1, 1, 1, 2. Okay, sir.
Okay. So if I only take these two vector, I will still get the vector space which I have started with. And so these two vector are linearly independent and they span this vector space. So what is the dimension of this vector space?
2.
This is 2. So what does dimension of vector space mean?
Cardinality
So-
of the basis.
Cardinality of the spanning set.
Not
Basic.
spanning set.
Basic.
It also has to be linearly
Number of
independent.
elements of cardinality of the basis.
Vector space.
So basically this is cardinality of
Basis.
basis. Now what is the basis?
Minimal spanning set.
Basis is
Which span the
basically
vector
a
space.
set which spans the vector
Minimal
space.
spanning set.
I will come to minimal and maximum later. Okay. So the definition of basis is must span the whole vector space and it must be linearly independent. Right? So this is the definition of basis. And can you please mute? So if some set which spans V and the set is linearly independent, then the cardinality of that set is basically the dimension of the vector space. Okay. So there is a difference between dimension of a vector space and the rank of a matrix. Okay. So what you are doing, who have started with the question, this one. So this is a subspace of R3, right? So let's get back to that question. So I am getting y minus y, z, y
Sir.
belongs to R. Yeah.
Sir, I will just take 30 seconds. As you were explaining the significance of rank of the matrix, we started your discussion from that point. That what is the significance of rank of the matrix? Because number of non-zero row in the row echelon form is a mathematical definition, right? So can we say that rank of the matrix helps us to determine whether the vectors are linearly dependent or not?
Exactly. That is the significance of the rank.
Okay. Thank you, sir.
That is the significance of the rank. Okay. Yeah. So now I am taking this set. Okay. And So if I take 1, minus 1, 0, 0, 0, 1, this set only. Is this set linearly independent?
Yes.
So let me, instead of S, let me write it as V, because this is a vector space. So these two are linearly independent, right?
Yes, yes.
This is clear, at least. Yeah. Okay. Now, is this set beta? Is beta spans V?
Yes.
Why?
Because any vector in V can be written as linear combination.
Exactly. So any vector is of this form. So I can write like this, right? So I'll get any vector of this vector space, right? If you are confused with y and z, you can write it in terms of a, b, c. That is also okay. So these are basically, so this answer is also yes. So beta is linearly independent and it spans V. What does that means? That means beta is basis of V, correct? And so the dimension of V is 2. Okay, is it clear?
Yes.
Yes, sir. Sir, I have one little doubt in a dimension,
Hmm.
sir. Sir, you said that in if we go upward, sir, you said that there is a dimension too, sir. And what I know now, the dimension is we say, let's suppose, number of the x, y, z component type. If we consider it's like a vector, then this 1 1 2, I think, let's suppose if we have the 1 comma 1, so there is a dimension 2. And if there is a 1 1 1 1 1, it means 4 time in 4. So sir, it means 4 dimension. Sir, shall you clear the how we know what is the dimension of any given vector space, sir? Because it's creating confusion, sir. What we
Again,
previously
I am
know, sir.
asking you the same question to begin with. Have you attended any live sessions earlier?
Yes, yes, sir. I
Because now at the end of this course, this question seems little bit, I mean, we don't really expect this type of question at the end of the course, right? So whatever you are saying, so inside of R3, can there be a subspace of dimension 2?
Yes, sir.
Who was asking that? Can you please unmute yourself?
yes, sir.
Yeah, Priyansh. So inside R2, R3, can there be a subspace of dimension 2?
Uh, no, sir.
Then what does subspace mean?
Sir,
So
subspace
forget it.
mean.
Forget it. So suppose I am drawing R2. So this is my R2, right?
Yes, sir.
R2 plane. Suppose I am drawing a straight line passing through origin.
Yes, sir.
Okay. Is this a subspace?
Sir, this is the line, sir. X is equal to y.
Whatever that be, x equal to some
Yes, sir.
my also can be. But
Yes,
is
sir.
this a subspace?
Yes, sir.
And what is its dimension?
Its dimension become 2, sir.
So
X and
suppose
y.
R2, I am starting with R2. This has dimension 2. This part is at least clear, right?
Yes, sir.
Okay. Now suppose I am taking this set. So if I am writing this straight line, I can write it. Suppose this is y equal to x line, as you were saying.
Yes, sir.
Okay. Okay. So I am saying xy such that y equal to x.
Yes,
Okay.
sir.
This is the
Yes.
straight line, right?
Yes.
Set of
Yes,
all
sir.
point on this straight line.
Yes, sir.
So let me write it as w. So you at least agree that this w is a subspace, right?
Yes, sir. Yes, sir.
Okay. Now let's find out what is dimension is. Okay.
Yes,
So
sir.
can I write this w in terms of this?
Yes, sir. We can write. We
Okay.
can write that.
Okay. So can you tell me a basis of w?
Basis of W is, sir. We can write 1 comma 1 also.
So is this set a basis of w?
Yes, sir. We can say 1 comma 1 or T comma T, sir.
So 1 comma 1 is a point and this set is a basis, right?
Yes, sir.
Because this has only one vector, so this is obviously linearly independent.
Yes, sir.
And this spans w, right?
Yes, sir.
Because I can get any point on this straight line using this.
Yes, sir.
Because all the points are basically scalar multiple of it.
Yes,
right?
sir. Yes, sir.
Clear? Till this one, this is clear?
Yes, sir.
What is the cardinality of this basis?
Cardinality of this basis, sir, 1, sir.
1. So what is the dimension of w?
Okay, it's 1, sir. It means the dimension is the cardinality of the vector space, sir.
Cardinality of the basis of the vector space.
Okay, cardinality of the
Okay.
basis of the vector. Okay, sir.
As
I
this set
understand.
is inside R2,
Yes,
every
sir.
point we must write it in terms of 2 coordinates. That is
Yes,
okay,
sir.
but that does not guarantee that it has a dimension 2.
Okay, sir. It
Is it
means that's
clear?
the yes, sir. It means that the number of the independent or dependent variable, number of independent variable.
Exactly,
Sorry, sir.
exactly.
Dependent.
Independent variable.
Independent variable. Yes, sir. I understand.
Exactly.
Thank you, sir. Thank you.
Got it, no?
Yes, sir. Sir.
Okay, great. Yeah, so is this clear to everyone?
Yes, sir.
Yes.
So I have explained this earlier also, but okay.
In this, when you're writing the dimension is 2, so
Dimension is 1.
above, so just
Okay. Nah,
just
dimension is
want
2.
to
Yeah.
find. So here, how many the independent variables and the dependent variables? Should we say dependent variables are 2 in this?
Independent variable. How many independent variables are there in this equation?
So
The
it looks
equation was x plus y equal to 0,
right. So it is 2 actually, yeah.
right?
But with dimension is coming 2, right?
Yeah, so no. My point was, see here x is dependent on y, right? And z
Correct.
is a constant,
Right. So
right?
that's
So
2
that gives
independent.
one dimension, and x is dependent on y, so that is again giving me a dimension.
Right.
So number of dependent variables means how many dependent variables are there?
1.
There are 2. I mean,
Depend.
dependent means also take the constant with it.
The constant is a dependent variable. Okay.
Yeah.
That's that was my query actually, because in this we have 2 dependent variables, right?
Yeah, 2 dependent variable and 1 independent variable,
Correct.
right?
So
Is it clear?
yes, sir. The basis will
Okay.
always be 2 in this, right? Because
So you can see now, basis means what? How many linear independence, I mean, in the spanning set, how many linear independent variables, independent vectors are there, right?
yes, sir.
So you have to write the basis. What is the basis of this set? Basis of this vector space.
Fine, sir.
That is two elements are there, right?
So my query was Z is a free variable, but I was a confusion. It is an independent variable, but it's a dependent variable. In this, right?
Yeah, I mean, Z is a constant, rather say that, without using the term free or independent in this case.
Oops. Thank you,
Okay.
sir.
I mean, Z can take any values, right here?
Z is independent, I think.
Z is independent, right? Z can take any values. That's what I am saying.
Yes, sir, yes.
Z can take any values,
Yes, sir.
right?
Then how are we getting dimension 2? They are 2 independent.
So that is the point. No. Okay. So again, let me start with it. Suppose I am taking this y minus y z. Y z belongs to R. Okay. So which variables can take variables freely?
Both Y and Z.
Both y and z, right? So when I am writing y as 1, z equal to 0, I will get one element of my basis, right?
Yes, sir.
And when I am taking y equal to 0 and z can take any value, z equal to 1 I can take, so I will get another element of my basis, right?
Yes, sir.
So how many elements are there in the basis? 2 elements, right?
2 elements, sir.
So how it came from? How many independent variables are there?
Yes,
right?
sir.
There are 2 independent variables, y and z.
Z.
Okay. And that's why the dimension of this vector space is 2.
Is 2.
Is it clear?
Learned is the number of dependent variables, right? Not and null space is the number of independent variables. That's what we learned, right?
But again, what is your question? I am not getting it properly.
Basis we learned is a number of dependent variables, and the null space is a number of independent variables.
No, that is different issue. So suppose you are confusing with all this concept all together. So what is null space? What is null space? Can you tell me what is null space?
Solution space of homogeneous.
It is
Huh.
is
Yeah.
space in the domain which gives 0 into 4.
Suppose I am taking x plus y plus z equal to 0 and say x minus z equal to 0. These are my two equations. And I want to find, so basically if I take this matrix, so this is my matrix, then solution space of this is basically the null space of A. Is this clear at least?
Okay.
Is basically
Yes, sir.
solution space. Okay. Now, can you tell me what is the dimension of this null space?
2.
What I have to do?
We have to find a basis, sir.
Basis of this solution space, right? So
Yes,
basically,
sir.
I will do the row reduction first. Okay.
We get the 2 comma 1 comma 0. Oh sorry. We get the 2 1.
What?
Sir, here we get 2 1 0 na sir at the finally, and we get one null space.
Yeah.
Null space, right?
So this is the row reduced echelon form, right?
Yes sir.
And I can substitute this as minus R2. Then I will get 1 1 1 0 1 minus 2. Okay. So what does it mean? X plus y plus z equal to. So
Sir,
again
plus
I
2.
can
Sir,
Sir,
plus
it's
2 sir. Plus 2
plus 2.
sir. Yes sir.
Yeah. So this is plus 2, and if I do this again, so R1 minus R2, I will get 1 0 minus 1 0 1 2. Okay.
Yes sir.
So what I am getting, x minus z equal to 0 and
0.
y
Y
plus
is equal
2z
to
equal to
2z.
0.
Yes sir.
Okay. So what I am getting from here, x is equal to z
Z,
and y is
and y
also
is equal to minus
minus
half of
2z.
2z.
Okay. So when I
Yes
am
sir.
writing x, y, z, which is in the solution space,
1 minus 2
so
comma
I
1.
can write, instead of x, I can write z. This
Z
is minus 2z.
minus 2z and z.
This is z. So how many independent variables were there?
One.
In the
Independent
solution?
variable only one sir.
Only one, right?
Yes sir. So dimension is 1.
Dimension is 1. Dimension of the
Okay
null
sir.
space is 1.
Thank you sir. Yes, we understand.
Is it clear? Sorry, 1.
Yes sir.
And now if I ask you what is the rank of this space?
Rank is
2.
2 sir.
Rank of A is 2,
Rank
correct?
2.
2 sir.
Yeah.
And null space is 0.
1 null space.
Null space is
Null
1.
Space is 1.
No, nullity is 1. Rank is
Nullity, yeah.
nullity is 0.
Dimension of null
Sorry.
space means nullity.
Uh,
This is the
Nullity
nullity.
is 1 and rank is
Sir, how null space is equal to 1 sir? I think nullity is 0. Yes.
Nullity is 1.
1.
Column minus rank is 1.
Rank nullity theorem.
Even we have just now find what is the nullity, right? This is the null space. So dimension of null space is nullity. That is 1, right?
Yes sir.
Yeah.
Yes sir. Yes sir.
Is it clear, no?
Yes sir.
Okay. And rank is 2. That is also clear, right?
Yes.
Yes sir.
So we have started with a matrix which is 2 cross 3, right? This is 2 cross 3 matrix, right? So rank plus nullity should be
3.
Rank plus nullity should is equal to 3 sir. Yes sir.
so it is satisfying, right?
Yes
This
sir.
is
Yes sir.
1, this is
It's satisfying.
okay. So what we are seeing, when we are solving this equation, then the number of independent variable is giving us the dimension of this null space. That means the nullity. Okay.
Yes sir.
Now what does this rank give? Rank is basically the number of remaining variables which are dependent, right?
Yes, sir.
So this dimension, this rank is basically a dimension of image space, right? So any matrix corresponding to some linear transformation, right? And I can call it dimension of image of T. So this rank is giving me the dimension of that image. Okay?
Yes.
And that depends on the number of dependent variable. Is it clear?
Yes, sir.
Is it clear to everyone?
Yes, sir.
Or do you have any doubt? You can ask.
Clear sir. It's a clear.
Okay. Any other doubt?
No, sir.
No sir.
Oh.
No, sir.
So you can ask me if you have any other doubts, not even in this section, but any doubt from this vector space dimension. Yeah.
Can we go on one by one? Some is this on
From?
Sir, today we have week 5 to week 7, right?
Yeah, but I am not going to do all the topics again. because that we have already done in every live session. So these revision sessions are supposed to be like you should ask your doubt and we should clarify it. Okay, I am not going topic by topic everything.
Yes, sir.
Okay, so if you have doubt, you can go and ask it.
Can we look at an AQ, sir? AQ, that is maximum equation.
Okay.
I have from the 6th week, sir. 6.1, 6th question.
Six
6th, sir. Yes, sir. 6th question.
Yeah. So this is linear transformation such that this is this. So how we are going to solve it?
Sir, I just what I did was just tried it out. 1 second. Sir. I'm just looking at.
So if you take the first option, what does that mean?
So
there are three vectors given, right?
So for none of the options, I thought that's why I was. So I checked all the 4 options, but I didn't like. He didn't.
So start with the first one. Okay. So what does this first option say? There are 3 vectors given, right? U, V, and W. And the images are basically U and V are going to 0, and saying that W is going to 5, 1, 0. So can this happen?
No,
that is the question, right? If this can happen, then there is a linear transformation like that. But can this happen for a linear transformation?
By applying, it's not coming, sir. It's not.
Okay. So let's start with. So what is E? U? 310, right?
Yeah.
What is V?
310. V 017.
017. What is W?
30 minus 7.
30 minus 7.
So if we take this U minus V, what we get?
30
minus 7.
30 minus 7.
So this is W, right?
Yeah.
Okay. So U minus V is basically W.
Correct.
Now, if there exists a linear transformation which satisfies all these properties, what should be T of U minus V? So T of W is basically your T of U minus V because W is U minus V. Now T of U minus V means TU minus TV.
TV, yes.
Yeah.
Right? So this is 0. Right? This is also 0.
Yes, sir. Yes, sir. Yeah.
So this is 0, right? So T of W must be this.
Which is not the case. Yeah.
Which is not the case, right?
Yes.
Is it clear? So there cannot be a linear transformation like this.
So sir, how TU is equal to 0, 0, 0? Maybe I missed something.
It is given.
Given in the question.
TU and TV both are 0, 0, 0.
Yeah, okay.
Clear, no?
Okay.
So there cannot be a linear transformation which satisfies all these 3 properties, that U and V are going to 0 and W is going to 5, 1, 0. Because if U and V are going to 0, then W also must go to 0. Okay? If T is a linear transformation. So this cannot be a linear transformation. Clear?
Yeah, yes, sir. Got it, sir.
So now can you do the second one?
So the same logic for the remaining, sir, or?
No, you have to check whether that is the case or not. Right?
So in fact, I tried it out.
Now try it out. Try with every problem. Okay. First of all, check whether U, V, and W are linearly dependent or independent. Check that.
You can just do for one, sir. The remaining 2 I will do just for the second option. Just for one.
So suppose you take the second one, 2, 1, 0, 1, 0, 1, and 3, 5, 6.
Yes, sir.
Okay. So you tell me what are UVW? I will write it. What is
Sir,
U?
in this case, you
210.
first, sir, in this case, if you should represent them in a matrix form and then row reduce and find out whether they are minimal spanning set, right? Then only we can.
Even this is 3 cross 3 matrix, so you can directly calculate the determinant if you want. That is also okay.
210.
210.
Hmm.
101. 356. Yes.
Okay. So if you write this 210, 101, 356. What is this? So 2, this is minus 5 plus 1, this is 3 minus 6. So this is anyway non-zero, right? So these are linearly independent. Okay? The determinant is non-zero, so this is linearly independent. Correct? Till this is clear?
Yeah.
So here we are taking.
So these three vectors are linearly independent, right?
Yes, sir.
Okay. Now what is given? What is TU?
Is equal to 10.
TU is 10.
And TV?
01.
And TW? What is TW?
We need to see that.
Yes,
I don't have that. Okay, 5, 6. Okay. Okay, so now this side we have started with R3. So T is a map from R3 to R2. Right? Now this UVW, is this a basis of R3?
Yes.
Yes.
Why?
Independent set.
Yes, sir.
So yeah, dimension is 3, and so there are 3 independent vectors. That means this is a basis of R3, right?
Yes.
And I am just giving some image to each of the basis element like this.
Correct.
Right? So this indeed a linear transformation, because what linear transformation does, if you just assign the images for the basis element, then we really know what the images are, what the linear transformation is. Okay?
But
so
we
here
have to check.
it is
But we have to check whether that is following a pattern or not. Right?
I mean, it is obviously it will follow the pattern, because we are just assigning images to each of the basis element, because they are linearly independent, no? So it obviously follows the pattern.
So, sir, one question: in any three, let's say it's speaking of R3 or R and whatever. So if you are able to find some n vectors, or here 3 vectors, and they are linearly independent, so immediately we can say that they are the basis, right?
Yeah, exactly.
Okay.
And if you assign the images for each of the basis element, then it is a linear transformation.
Okay, we are applying the transformation for basis, and the result that you get is the linear transformation. I mean, what are these three? These three would be now 1 0 0 1 5 6 could be.
I mean, we just here we have R3, and we have taken 3 linearly independent vector, and we have assigned 3 images for them. So
Yes,
that is indeed a linear transformation.
All elements of basis are having images, right, sir?
All the elements have some images.
Yes,
and
of basis. Yes.
Yeah.
Sir, how did we conclude that TW will be the correct image?
I mean, there does not we need not really have to compute what the image of W be, because this U, V, and W are linearly independent. Okay. So there is no such relation between U, V, and W. Okay. So whatever the images I can assign there. Right? That's why I have started with checking whether it is linearly independent or not. If in the earlier case what we have seen, this W is linearly dependent on U and V, right? So I have a relation like this. That's why we have to check this relation. But now in this case there is no such relation, because these are linearly independent. So whatever the images we need, we can assign there.
Okay, so can we say that if the nullity of this matrix is 0, since this nullity of the matrix is 0, that is the
What is the nullity of this matrix? Which matrix?
No. So I am saying if you take these three vectors, okay, their nullity is 0. If because the R3 to R2 transformation. So what is the rank nullity if I compute that according to the rank nullity
Rank nullity of
theorem?
what? I have not computed rank nullity for T. Okay, I have just written this vector as a matrix and for calculating the linear dependence or independence. So nullity of this matrix is 0, but that has nothing to do with this linear transformation. That has nothing to do with this linear transformation. Is this clear?
Yes.
Sir, can you hold 1 minute, sir? The last line which we got the results. So here the 3 in R2 that we got the 3 images, that is for the transformation UVW. These 3 will, is there any significance for that? Or it's just 3 vectors in R2?
Any 3 vectors in R2 you can write here. That will give you a linear transformation. Okay.
But these need not be the
basis.
These are bases in R2, right? These 3?
No, this may not be a basis in R2.
May not be. Okay, may not be. Okay.
I mean, this is not a basis even.
Yes, sir. Yes, sir.
Right? Because there are 3 elements. This cannot be a basis of R2.
Yeah, correct. Yes. Thank you, sir. Thank you.
So even I can take all the UVW and just assign everything to be 0. That is also a linear transformation.
Yes.
This is also a linear transformation, right?
Yes, sir.
This is a linear transformation, basically 0 transformation.
Yes.
Okay.
Yes. Thank you.
Yeah.
Sir, just a small request, sir. Of course, it is your prerogative to decide how to drive the session, sir. But it will be great help if you can, go topic wise, sir.
Go back to the earlier live session and watch that.
Of course, we will do that. Like just I'm not saying that a complete revision, but just the important concept. That will be a great help. And then in between we can ask our doubts. Like if we have any question related to a particular topic. It is just a request, sir. I'm not saying that's why at the beginning I told that it is your prerogative how to drive the session. It's a small request, nothing else.
Okay, let's see. Let's first clarify all of your doubt on this. Okay. So till this point, is it clear?
Yes, it is clear.
If we have a basis and if we just assign this thing, okay. This is clear, right?
Yeah, clear.
So actually, sir, it is not, you do not go by any linear transformation definition. You are saying basically that 3 input vectors are linearly independent. That is the reason there should be a linear transformation exist.
No, that is not what I am saying. I am saying I have this domain part, I have a basis. Okay. And so basis means here in R3 I have 3 independent vectors, right? And I am assigning some value to that, right? Now my claim is this is a linear transformation, right? So how I am claiming this? So what does linear transformation say? Linear transformation says that 0 must go to 0, right? And it satisfies the linearity property and the scalar multiplier property, right? Now any element of R3 can be written as a linear combination of this, correct? So
Yeah, we can write it, but how you can prove it? Means we can always. So if it is a R3 to R10, what you will say? T equal to R3 to R10.
So
then is it a linear transformation?
Why not?
No. So that is the reason I am asking you. How you prove it?
That's what I was doing. Suppose, say in R3, I have this XYZ as my one vector, right? The general vector, correct? So I can write it as C1 U1, C2 U2, and C3 U3, right? Correct?
Okay.
So can you first determine what is C1, what is C2, and what is C3 from the given equation? So let's try to write it. Okay. What is U1? What is U? So here UVW, let's write that. UV and W. So 210. What is C2?
101.
1 0 1 C3
356.
356, right?
Mm-hmm.
So can we determine what is C1, C2, and C3 from here?
Yes, because there are three equation, three unknown.
Because it is 3 unknown, okay? So if we write this, so 2C1, C2, and these are linearly independent, that is the main point
Yes,
here.
correct. That you have proved.
Okay, so C1 plus 5C3 and C2 plus 6C3, right?
Yep.
So all these are in terms of XYZ, linear terms of XYZ, right?
Yes.
So if we just do it, this is X, C1 plus 5C3, this is Y, C2 plus 6C3, this is Z, correct?
Mm-hmm.
Okay, now can you solve it? What is C1, C2 and C3?
Yes.
So let's solve it. Okay, so what I can write it from here? Anyone?
R1 by 2.
R1 by 2, let's start with that. Then
R2 minus R1.
so 0 minus half, 5 minus 3 by 2, so it is 7 by 2. So y minus 6 by 2, right? 0 1 6 Z. Okay. So then what I should do?
So we can avoid these radicals by doing R1 and R2 to start. So too many radicals.
Huh?
So we're getting too many radicals. So we're getting too many radicals in the equation. So we can start with R1 minus R2 and then do it. It will be easier. No?
Whatever way you are doing, just solve this equation. That is any way you can. Okay, so this is I am following the usual Gaussian elimination method.
Minus 7.
So x minus 1. Okay, 0 1 6 Z. Okay, I am doing right till this point.
Yes.
Yes, sir.
Okay, now what should be the case?
R3 minus R2.
Okay. So 0, this is 0, this
13.
is 13, right? And
Z minus
Z
X
minus X plus 2.
plus 2y.
Okay. Okay, so 13 C3 is basically Z minus X plus 2y. So C3 basically Z minus X plus 2y by 30, right?
Yeah.
C2 minus 7 C3, that is X minus 2y. So C2 equal to X minus 2y minus 7 Z minus X plus 2y by 30, right?
Plus 7.
Plus. So 13x minus 26y plus 7z minus 7x plus 14y by 30. Right. So it is 6x minus 12y plus 7z by 30. Okay, this is C2. Now can we solve C1 from here? C1 plus C2 by 2 plus 3 C3 by 2 equal to x by 2. So So from here I can get what my this is, right? C3 is z minus x plus 2y by 1326. This is minus, right? So if you solve this, so 26x minus 6x plus 12y minus 7z minus 3z plus 3x minus 6y. So
The
Should be 13.
13x there, 13x.
where?
First term,
First
first term.
one.
13x. Okay. So what I am getting? This is 7, 10x, right? And y is 6y and minus 10z by 26. And that means 5x plus 3y minus 5z by 30. Okay, so we got C1, C2 and C3, correct?
Yes.
So I can write x, y, z. This is my C1 into u plus what is C2? 6x minus 12y plus 7z. 6x minus 12y plus 7z by 13 into v plus that C3 z minus x plus 2y z minus x plus 2y by 13 into w, right?
Yes.
This we got. So I have to find what t x y z is, right? Now these are
Yeah.
constants, so this is tu, tv, tw, right?
Yes.
Because x y z was t x y z, c1 tu, c2 tv, c3 tw, correct? That's
Yeah.
what I have written here, right? Now we know what tu is, correct?
Yeah.
We know what this is. And we know what this is. This is 5,6, right?
Yes.
It was there. 5,6. Right? So now can we write what these values are?
Plus is 5 and
This is the first coordinate, and the second coordinate is 6x minus 12y plus 7z by 13 plus 6z minus x plus 2y by 30. Right?
Yes.
So what I am getting here, 5x minus 5x cancel out, 3y plus 10y, 13y,
13y.
minus 5z plus 5z. So this is cancelled, 13y by 13. Okay. And what is this one? This is 6x minus 6s cancel out, minus 12y
plus 12
plus 12y, right? So it cancel out, 7z plus 6z, 13z. Right? So this is y comma z.
Yeah.
Okay. So basically t x y z, which by all this calculation after we are getting just
Y
this
comma.
linear transformation. Now can you check
Yes,
whether
sir.
that is
This is true. Yes, it will follow all the three linear transformation properties.
Right.
It has So 0, 0,
So
it has
basically, in
an,
this process, do you see a proof of this?
Yes, yes.
Basically, this is the proof. This is a particular example,
So
but in general, if we do, this is the exact same proof.
correct.
Can you see it?
That point was new to us. The independent set will always be transformation.
Exactly, because if we start with some linearly independent set, okay, of the same number of elements. So suppose in R3, I am starting with 3 vectors which are linearly independent. That means that forms a basis, right?
Yes.
So any element of my R3, I can write as a linear combination of that. That linear combination is important. Okay. Now, whatever the image you assign there, that will give you a linear transformation, right? Because you are doing it in a linear way. Because when you are expressing an element of R3, that as a linear combination of those 3 elements to which you are assigning your images, right? So it will always be linear. That is by default. Okay, is it clear?
Yeah.
Is it clear to everyone?
yes.
Okay.
Sir, if TU here it is given as 1, 0. Now, if the TV is also given as 1, 0.
Then also no problem. Right?
Then
What
also the this will hold.
The linear transformation will be different, but there will be a linear transformation.
Okay, so means what is the theory we got? We got a theory that if this is an R3, okay, so here the basis, the given basis is a R3 basis. So R3 to R2, so means what theory we got actually? This is a pretty interesting thing. That is the reason I'm.
Basically,
So,
what I have
if
started
I
with,
get it,
if you just have a basis for your domain, you assign to each basis vector an image that will give you a linear transformation. Is it clear? If for your domain you have some basis vector, basis set. Now for each of these basis vector, you are assigning some images there. You will get a linear transformation.
Or if we have an image for each of the vector of the basis, then we can define the linear transformation as a
that's
combination of.
correct.
Exactly.
Yes.
Okay. Clear, no?
So what we are saying
Clear.
basically is, so my clarification is like when we are applying the transformation to the basis in the domain, what you get is a linear transformation, right?
If you exactly. If you give your assign some images for your each basis element, you are starting with a basis for your domain, right? And
Otherwise, it's transformation. Image, when we make image, basically it's transformation, right? For the basis.
Yeah.
We are applying the transformation to the basis, right? That's the.
What you are saying?
No, sir, we are saying for the image, when you're talking about image, rather than saying image, we are applying the transformation to the basis.
No, to begin with, there is no transformation. That is the point.
Okay.
I am assigning some images for those elements, basis elements. Okay. That is giving me a map, and that map is a linear transformation. That is my point.
Okay. So assigning this randomly, how will you assign without like any proper some kind of algorithm, right?
Because you are starting with a basis on the for your domain.
Okay, that's what I was thinking. So we'll start with the basis in the domain, right?
That is what I am saying from the beginning.
Okay.
Is it clear? So whatever the linear transformation you got here, is it satisfying all those property? TU, TV, TW? It is satisfying, right?
It is.
Okay. It is satisfying, yeah. So that's how we basically are getting linear transformation from a basis. Okay.
So this question was all about only whether finding the domain are independent or independent.
Exactly. Now if you see the rest of this. Now the third one. Now third one is an interesting. You have UVW and all of them are going to 0, right?
Yes, sir.
And there is a fourth vector, 1, 4, 2. That is going to 2, 4, 1. Now, can this be a linear transformation?
Cannot be,
Why?
because that is a combination of the first three vectors.
Yeah, because this UVW again, they
We
are
have to say
linearly independent, right?
Yeah.
UVW forms a basis and all of them are going to 0. That means this is a 0 transformation.
Yes.
Right? So the fourth one, whatever the vector you choose, that also should go to 0, but that
Yes.
is not the case. Got it?
Yes.
Yes, sir.
Yes.
Great. Good. Okay. Last one is quite clear. What about the last one?
Yes, it follows from the second one only. You have a
It's again a
Ag-
standard basis, then we can.
Again, it is a standard basis, so basically you can write the linear transformation. So for the last one, can you write down the explicit linear transformation as we have done it for the option 2?
Yeah.
Yeah, yes, sir.
Yeah. So what will that be? So
First,
let me
we
write
write
it.
any vector in R2 in terms of.
So this is what we want, right?
Yeah.
TR2. So what should we do?
XY is equal to
XY is
x
some linear
times
combination of 1,
x
0 and.
times
Then what is C1 and C2 here? In this case, this is
x
quite
and y.
easy, no?
X and y.
X and Y, right? Is this clear to everyone?
Yes, sir.
Because this is the standard order basis, right? So T of xy is basically T of this and T of this. So x, pi, comma 1, 1, comma e, right? So
Yeah.
this is pi x plus y, x plus e. This is your linear transformation.
Yes.
Okay? Clear now?
Yes.
Yeah.
Okay, great.
Sir, can you please scroll up a bit?
This one or no?
Sir, little
Is
bit
this
more.
okay?
Yes, sir. Yes.
So, sir, last one I can directly say from your hypothesis that you have just derived that since
Exactly,
it's the basis is
Exactly.
given, so
It's clear, no?
yeah.
Okay.
Yes, sir.
But every time you teach, we learn a different thing, well, new thing.
Yeah. Okay. So I hope this is clear. Any other doubt you want to ask?
Sir, I think it's t x comma y is equal to pi to the power x and e to the power y, isn't it?
E to the power.
Pi to the power x and e to the power y.
No, pi x. That's all. It's multiplication, not power.
These are multiplication, right? Pi into x, e into y.
No, sir, can it not be?
Oh, so you are giving another one. Okay. So let's see pi power x and e power y.
Yes.
Right?
This is not
This
linear
is what you
transformation.
are. What is t 0, comma 0?
T 0 comma 0. Oh, okay, sir. It's a no. It's a 1 comma 1.
So it is not a linear transformation, right?
Yes.
So linear transformation always must be some linear combination of your variables.
that it will become an exponential transformation.
That what that means I don't know, but anyway, so when we are talking about exponential transformation, exponential function I know. What is exponential transformation?
It's a new term.
Yeah. So
Sir, how about if we write it as pi power x minus 1 comma e power y minus 1?
So what is the result for this one, sir? I didn't understand. So it means that the transformation.
It is
Pi
a
x plus
one by
transformation.
one by
Yeah. Okay, got it. Nice.
You got it, no? Okay. Then yeah, next one. Who is asking this?
So this is a transformation.
This is a transformation, right?
Yes, sir.
I mean linear transformation.
Pi x plus. Yes, sir. Pi x plus.
The linear combination of x and y is there, so it's obviously a linear transformation.
Yes, sir.
Right? Okay. So, yeah. So any other doubt till this point? Anyone wants to ask? No?
No, sir.
Okay. Okay. So let me see. So if you are given some span of some set, okay, some say V1, V2, V3, and V4, where I am giving you an relation V1 plus V3 equal to V2 plus V4. Okay, I am giving you this as my vector space. Can you tell me what is the dimension of V? You understand the question, right? I have given you a set V1, V2, V3, V4 with a relation that is V1 plus V3 equal to V2 plus V4.
Sir, I think it's a 3.
Okay. Okay, I am coming to that. So I am taking the span of this set. This is my vector space V. So I want to know what is the dimension of this. Already one of you are telling it is 3.
3 or less than 3 also.
3, sir, 3.
So, can we less than 3? 3 and less than 3.
No, because
Why?
there are one independent, one dependent variable, so it should be 3.
So,
Okay. Who is saying less than 3?
yes, sir. I say.
Yeah, why?
So because we can write like V3 in terms of V1, V2, and V4. So V3 is dependent. So maybe two vectors are dependent there. So in that case,
Can you tell it little more clearly? What you are doing here?
so sir, how can we say that only one vector is dependent?
Bread আনবো কালকের জন্য
Because we can only if we forward B3 in the other side, then it will be V1 is equal to V2 plus V4 minus V3.
Okay, sir, I got it, sir. Because
Basically, I can write V4 in terms of this, right?
Yes, sir. Actually, I was thinking something else. I got it.
And there is no other relation given. So we are basically assuming all these V1, V2, V3 are linearly independent, right? We are assuming that these are linearly independent. No other relations are given. So I can write it V2, V3, and this I can write like this. Okay. Now if point is if this V1, V2, V3 are linearly independent, then dimension of this V is 3. Correct? Because span of this set is basically same as span of this 3 element V1, V2, V3. Right? Is it clear?
Yes,
sir. Sir, how to check linear transformation is into or onto?
But sir, if V1 plus V3 is equal to V2 plus V4 here, so we can express that the linear combination as twice V1 plus V3, right?
How?
Yes, sir. To get a vector, any vector in V, V1 plus V3 is anyway equal to V2 plus V4, right? So we can just mention as 2 times V1 plus V.
2 times?
V1 plus V3.
Is what?
Is any vector. We will not take V3 and V4, V2 and V4 or whatever. Any vector will be V1 plus some combination of V1 plus V2 plus V3 when V4, right? But here V1 plus V3 itself is V2 plus V4, so we can substitute, right?
Yeah. So
the dimension, how do could it be lesser than 3?
No. I mean, what I am saying, so this relation, what does this relation mean? Suppose I am keeping my V4 in this side and taking all the other in the other side, okay? So V4 is basically V1 plus V3 minus V2, right?
Yeah, I got it, sir. But I was thinking like for the four vectors, rather than expressing a V1, V2, V3, V1, V2, the remaining two can be expressed as
How you can express using one equation two vector in other two other term?
1 plus.
So among these four, you have to express. You want to express two in other two, right?
Yes, sir.
So
Yes,
what
sir.
is your V1 can be?
V1
Can you express
be,
V1 in terms of only two vector?
no.
No, right?
No. Yeah.
We always need three vector.
We need three. Okay, got it.
Got it, no?
Yes, sir. Yes, sir. Got it.
So V1, V2,
Because
V3.
at a time we can there can be only one vector, one dependent vector and three independent vectors.
Exactly.
So V1, V2, V3 are linearly independent. It is given here, or we are.
No, I am assuming it. I am assuming it if these are linearly independent. Then we can say the dimension is 3.
Yes.
Okay?
So
Yeah.
what if V1 is equal to V2 and V3 equal to V4?
So let's do that. So span of V1, V2, V3, V4. I have two conditions here, right?
Yes, sir.
You are saying this, right?
Yeah, yes, sir.
So I have two conditions. Then I can write this in terms of V1, V2, let be as it is. V3 I can write as V1. This is as V2. Right? So basically I am repeating these two elements. So don't need to repeat that. So basically V1, V2. Right?
Yes,
now
sir.
if this V1 and V2 are linearly independent,
Then 2.
Then dimension will be
2.
So it can be 2 also, right, sir? So it can also be 2, right?
If these are the relation.
Okay.
So this should be given in the question. Then we can
No,
say
even
that
without it given in the question, we can by assuming that it can take a minimum dimension of 2, right? So if they ask what will be the minimum.
No, this condition, only this condition and this are linearly independent, that assure that this cannot happen. Right?
Okay, but
if this
it
happens, then
being
is
linearly
V1, V2.
Okay.
1 minute. If V1 equal to V2 and V2 equal to V4, is V1, V2, V3 linearly independent?
Sorry, sir. Can you come again?
If V1 equal to V3 and V2 equal to V4, is V1, V2, V3 linearly independent?
No, sir. They are
They are not, right?
Yeah, they are
so
not.
So when I am claiming the dimension is 3, I am assuming that V1, V3 are linearly independent.
Yeah, this is us assuming, right, sir?
Yeah.
Yeah, and the same goes for V1. No.
So even if we don't assume it, even suppose V1 is 0, that also can happen, right?
Yeah, that can also happen. Yeah.
Right. So that's why.
So suppose this is asked in a. Suppose this is asked in a question, then we'll get this.
It will not be asked in this manner. This is just for clarification of your concept.
Oh,
okay.
This I mean, I will not directly ask this question, right?
Okay. But if it is asked, then this condition is important that V1,
yeah,
V2,
obviously,
V3
this
are
really independent thing is important. Otherwise, you cannot conclude anything from here.
Yeah, so because all the 4 can be a 0 vector and the V itself can
be V can be 0. Yeah, exactly.
Yeah.
There are many possibilities are there.
Yeah, definitely.
Right?
Thank you, sir. Yeah.
Okay. So So let me just recall what linear transformation is, TV to W. Then I will come to one-to-one and onto linear transformation. So what is linear transformation? So basic definition is quite clear. 0 is going to 0. That is one thing we need to check to begin with. And if we have this condition, say alpha V plus W, V1 plus V2 is basically, so let me write it into separate TV1 plus TV2 and T of alpha V plus alpha of TV. Right? This is for all V1, V2 in E. And this is for all alpha in real and V of 2. Right? This is the definition of linear transformation. Correct? So suppose I am giving you an example like this, R3 to R2.
Also, the 0.
0 is going to 0. That is quite implicit from this condition.
Oh, okay.
The 0 is going to. Okay. Okay. So suppose I am defining this. Is this a linear transformation?
Yes.
Yes, yes.
So you can check those conditions and you can say this is a linear transformation. Okay. So now I have a basis for R3. Okay. Suppose I am taking this as my basis in R3. Okay. And on the right side, I am taking the standard order basis for R2. Okay. So there is a matrix corresponding to this linear transformation with respect to this basis. Right? How can we determine that?
Take the images of the basis and then express it as.
So what is this image? 1. This is -1. This is -1. This is 0. This is 0.
1.
This is 1, right?
Yeah.
So if I want to express this in terms of this, so what, this is exactly the same thing I will get, just coordinate wise. So what is the matrix I am getting here?
1 minus 1.
1 minus 1.
Minus 1,
Minus 1, 0.
0, 1.
So this is a 2 cross 3 matrix, right?
Yes.
So 2 cross 3 means it is from R3 to R2.
Yeah.
Right? So I am getting 2 cross 3 matrix. Okay. Now let us calculate its null space. What is null space is of the transformation? Null space of T. What does null space means?
Sir, I have a basic doubt. Okay, so just before this exercise, we told that if the basis image is available, okay, then that is a linear transformation. So this is also holds for here because the 1 0 0 1 1 and 1 1
This is
0.
already I am giving you a
These
linear
things are
transformation to
available.
begin with.
Yeah. Sorry, sir. No. Sorry, sir. It's some related. Sorry, sir. Yeah, you go ahead.
Okay. So yeah, null space of T. What does null space of T means?
1.
No. What is the definition of null space? Let's start with that.
The space in the domain which gives 0 in the column.
So this is the thing, right?
Yeah.
This is going to 0. This is null space of T in this case.
Yes.
Right? So because we are dealing with R3, so null space is inside the domain. So this is the domain. So this is the codomain. So null space is somewhere here, right?
Yes.
Which is going to 0.
0.
Here somewhere is 0 of the codomain, and this is the null space, right?
Yeah.
Okay. So basically T of x, y, z. Here I have taken x minus y and y minus z. So if this is going to 0, 0, that means what? X minus y is 0 and y minus z is also 0, right? So what does it mean? X equal to y and y equal to z. So x, y, z, null space of T. What can I write this set? This is x equal to y and y equal to z. That means x, y and z are equal, right?
Yes.
X
All
equal
are
to y and y equal to z, and x, y, z are equal. So this is basically x comma x comma x.
yes.
Is it clear?
Yeah.
Yes, sir.
So what is the dimension of null space?
1.
1.
It's clear, right?
Yeah.
Okay. So this is basically nullity. Dimension of null space is nullity of T. Okay. Now what is rank of T?
It is 2.
Okay. So basically we know rank nulity theorem. From there we can directly calculate it. Dimension of the domain.
Domain.
Domain is V. Here it is 3. So nullity is 1. So rank T plus 1 equal to 3. That means rank of T is 2. Right?
Yes.
Now what does rank mean? Rank means basically dimension
Number
of the
of
range space.
Image.
Rank of T is basically dimension of the image. Range space should be the better term. Range
Range.
of T. Okay, this is a now basically here these are basically my images in R2. So as it is of dimension 2, that means it is taking care of whole R2, right? Every element of R2 is in the image.
Yes.
Is it clear?
Yes.
Yes.
Yes, sir. Yes.
So what does this basically coming as? So this is my R3. This is my R2. Here something which is one dimensional space. This is my null space. Null space of T. So this term is going to 0. All this term. This is going to 0. Now you have calculated rank as 2. So dimension of the codomain. Codomain is R2. This is 2. The range space is inside that. This range of T must be inside this codomain,
Correct.
which has dimension 2. Right? That means range space is basically the whole space. Because range space is a subspace of R2 which has the same dimension. That means the range space is range of T. This is the whole R2. So basically range and codomain are same in this case.
Yeah.
Right? So this T is
Onto.
yeah, T is surjective. Clear? This is clear?
Yeah, yes, sir.
Okay. Now go back to this matrix we have came across. So this is the matrix representation of T.
So then explain the onto again, that's confusing.
Huh?
The onto one.
So range, whatever the range means set of images, right?
Yes, sir.
Whatever the range is, this is inside R2, right? Inside the codomain. R2 is my codomain, right?
Yes.
And we have calculated the rank of T. That means the dimension of this range space is 2. Correct? What does it mean? Range space is a subspace of R2 which has same dimension as the whole vector space. Right? That means if we write it like this, suppose W1 is subspace of W2. This is subspace. And dimension of W1 and W2 are same. What does it mean? It means W1 and W2 are the same space. Okay? Because suppose this is W1, this is W2, this is W1. It is inside. Now if the dimension of both are same, that means what? These both the subspaces, both the spaces are exactly the same.
Same.
Clear?
Yes, sir.
So what does it implies here? That range is basically whole R2. Okay? So range and codomain are same. That means T is on.
Okay,
Yeah.
in codomain same means we are onto.
That is the definition of onto, right? Range and
Yes,
codomain are
yes,
same.
yes.
Yeah. So it is clear, right?
Yes, yes.
Okay. Now go back to the linear matrix 1 minus 1 0 minus 1 0 1. So this was the matrix 1 minus 1 0 minus 1 0 1. This was the matrix we got. Now in matrix also, now treat it as a separate matrix here. all together A. Now, if we want to calculate the null space of it, let's see what happens. So what 2 plus R1, right?
Yeah.
0, 1,
Minus
1.
minus 1. Second is
Minus 1, 1. Right? And what we can do here?
into minus 1. R2 minus.
So this is 1 minus 1, 0, 0, 1 minus 1. Then one more step I can do. R1 minus R2, R1 plus R2. So 1, 0.
Minus 1.
Okay.
Yeah.
So if you want to calculate the null space, x plus x minus z equal to 0, y minus z equal to 0. So from here x equal to z and y equal to z. That means again x and y and z are equal. So the null space of A is x, x, x. Again, which was exactly the null space of T, right?
Yes.
So that is the significance of this matrix representation. If we calculate the matrix representation and find out its null space and rank, that will be same as the rank and nullity of the linear transformation. Okay, because here also nullity of A. Nullity of A. What is nullity of A? Because dimension is 1, so it is 1. And after row reduction, there are 2 non-zero rows, right?
Yes.
So rank of A means
2.
So this is same as the nullity of T and rank of T, right?
Is also true. Yeah.
But sir, if we have the null space of A and we want to find the null space of the transformation, you have to multiply this null space with the basis to get the null space of the transformation.
What does that mean?
We have the null space of the matrix. We have to multiply each element of the null space of matrix with the basis of the
No, null space
domain.
of the matrix and null space of the linear transformation is the same. That is what I
But if
said.
you want to find the basis of the null space of the transformation, then don't we have to multiply the basis? Don't we have to multiply the null space of the matrix with the basis of the transformation to get the basis of the null
Basis of the
space?
transformation.
Yes, basis of the domain of the transformation.
Why? See, null space is this thing. What is the basis of this null space?
1, 1, 1.
1,
1, 1, 1, right?
Yes.
Correct? Basis of this null space of A. Is 1, 1, 1, right?
Yes, yes.
And what is the, so as null space is the same, exactly the same. So basis will also be the same, right?
Yes, yes.
So why this all these are coming? I am saying these bases are exactly same. So the basis will also be the same.
Yes.
Okay.
No, but in the lecture, sir said that if you want to find the basis of the null space of the transformation, you have to multiply the.
No, sir has not said that. You have confused with some other thing, maybe.
Okay, okay.
Sir, the null space vector will be expressed with respect to the chosen basis for the domain of the linear transformation.
Yes.
That is separate issue. That is separate issue. Yeah. Definitely. So if from a given basis from R2, if you have to choose which are going to 0, then you have to do all this thing. Okay. But here I am doing it in general. Okay, I have given you a linear transformation. I am asking you to find one basis for the null space. Then this is the way you can do it. Okay, whatever the basis for the null space of this matrix and whatever the null space of this linear transformation, those are exactly the same thing. Okay, is it clear? Is it clear?
Yes, sir.
Yes, sir.
Okay. So, and when a linear transformation is 1 to 1,
When the nullity is 0.
when the nullity is 0, that means when the null space is 0. Null space is the 0 vector space. Okay. So let me write it. 0. Okay. Null space is 0 means the nullity is also 0. So suppose I have a linear transformation from R3 to R4. Okay. So my question is, can it be 1 to 1?
Yes,
It can be.
it can.
So why are you saying that it can? So give me an example.
Because example.
So you say there can be a linear transformation which is 1 to 1, right?
Yeah.
So give me an example which is 1 to
1. XYZ is equal to XYZ 0.
It
Okay,
cannot
so
be
you are
1 to 1.
giving
No?
me this example, right?
Yeah, equal to XYZ 0.
So actually, sir, it can be. It never be 1 to 1.
Why? Is not this 1 to 1?
No.
Why? What is the null space of this? Null space of it?
Null space is 0.
No, null space of it will be 0, 0, 0, T.
0, 0?
T.
P.
T means in the W. Oh, sorry. It will be 0, 0, 0.
And sir, we can also say that like the matrix correspond to this linear transformation is, of the order 4:3. There,
So?
there we can also say that the 1-to-1 relation is possible.
1 to 1 is possible because this is already he has given an example. You have XYZ equal to 0. So if we calculate this null space, it is indeed 0, 0, 0, right? Only the 0 vector is in the null space.
Yes, sir.
Correct?
Yes, sir.
No other area. So the nullity null space is indeed 0 vector space. So nullity is 0. Yeah, correct. What is the rank of this?
3.
Rank of it is 3. Okay. So it can be 1 to 1, right?
It can be 1 to 1.
Can it be on 2?
No.
Why?
Because the rank is less than the dimension.
Rank must be less than dimension. So dimension of what?
Codomain is not the range.
Codomain is more than dimension of domain.
So if we use rank 90 theorem, this is dimension of V, right?
Yeah.
So V is here 3.
3.
Okay. So rank, whatever nullity is, rank must be less than equal to 3, right?
Yes.
It cannot be greater than 3. But if it has to be on 2, if T has to be on 2, then rank of T must be
4.
4.
Which cannot happen, right?
Yeah.
Yes, sir.
So it cannot happen. So T can't be on 2. Clear?
Yes.
If we change R4 to R3, can it be 1 to 1?
Cannot.
Why?
Because the domain dimension is bigger than the.
Again, we will take rank 3 plus nullity T is 4. Now it is 4, right? Dimension of this is 4. Now if nullity is 0, if T is 1 to 1, if T is 1 to 1, then nullity is
0.
Nullity is 0. Then rank is
4.
Then rank of T must be 4, which cannot be the case, right?
Yes.
Because dimension of the codomain is
3.
3. So it cannot be the case. Yeah.
Yes.
Is it okay? Can it be on 2?
1, 2.
Can
Yeah.
it be on 2?
It can be on 2.
Can you give me an example? R4 to R3, right?
Yeah.
Can you give me an example? Where it
Same
is on
example
2?
in the reverse direction.
Yes, same example. XYZW equal to XYZ.
Yeah. Right. Clear, no?
Yes.
Okay. Okay. So more or less it is. So any more doubt in rank 90 theorem and 1-1-1-2 linear transformation?
Actually,
So
sir,
the basic point
actually,
is you can, yeah.
sir, the on-to and one-to-one on-to is a bit confusing for me, sir. Actually, I've been having to try to get a hang of it, but it's quite difficult for me to get in terms of these transformations. Onto one.
So what do you understand till now? I mean, what is 1-to-1, you think?
So I am looking only from set theory, which is slightly simpler, but in transformations, I'm finding it difficult to understand.
Forget transformation. What is set theoretically? What when a function is 1-to-1?
So, like you have, let's say set A and set B. So, for each element, you will have a unique element in the code. Mapping to a unique element in code.
That is always the case, no?
But in transformation, I'm not able to.
No, I mean that is
It's very confusing.
the basic definition of mapping. That is not 1-to-1.
Because the connect the link between the transformation being onto
Forget transformation. What is 1-to-1 mapping?
Yes, sir. For domain, I mean for unique for unique element in domain, we have a unique mapping for code.
That is always the case.
For each element in domain.
Codomain may have more points. Codomain may
No,
have
sir,
more points.
I'm talking about 1-to-1, sir. 1-to-1. So 1-to-1, let's say X is in domain. So we are taking F and F of X will give Y, which will be unique. Y will be unique.
I mean, this cannot happen anyway, right? This is not a function.
That's not possible.
No, I'm not talking about this, sir. This is not a function at all. I'm talking about
Exactly, right.
I'm talking about 1-to-1. 1-to-1 is like you have elements in your domain. So distinct elements when domain will map to distinct elements in code.
Exactly. So two elements of the domain cannot go to same element. This cannot happen.
Yes.
Right?
Yes.
Yeah. Same definition for linear transformation. Okay. Two elements of the domain cannot go to a single element. Okay. That is the first definition for 1-to-1. For linear transformation also, that is the same thing. T V2W T V1 equal to T V2 implies V1 equal to V2. If this happens, then T is 1-to-1. Right? This definition you know for mapping, correct?
Yes.
This is the same thing. Same thing for linear transformation. Now, linear transformation give you a further advantage because here everything happens linearly. So, from this definition, we can derive that if only 0 is going to 0, no other element is going to 0. If that happens, then T is 1-to-1. Okay. So if some other non-zero vector, suppose V is some non-zero vector, if it is going to 0, then T is not 1-to-1.
Not 1.
Okay.
Not 1-to-1. So there's some noise.
What does that mean?
Background noise.
Okay, so T is not 1 to 1. Now, what does it mean? It means that the null space means which vectors are going to 0, right?
Yes, yes, sir, yes.
All the vectors which are going to 0. Now, when T is 1 to 1, that means null space must be 0. Only 0 is going to 0. No other
Yes.
element is going to 0. Right?
So
That is the
yes.
definition we have taken.
Yes, yes,
Right? So, when null space is 0, then T is 1 to 1. And vice versa. Okay? Clear? Till this point
Yes.
it is clear?
Yeah, this is clear.
Now what null space 0 means? So null space is a vector space. So nullity is its dimension, right? Nullity is the dimension of null space. Correct? That is the definition.
Yes.
Nullity of a transformation is basically the dimension of the null space. Okay? Okay. Now when null space is 0, what is its dimension? What is the dimension of 0 vector space?
0.
0.
0. So that means nullity is 0 if and only T is on 1 to 1. Clear? Till this point it is clear?
Yes, sir. Yes, sir. 0 transformation.
Clear, no? Okay. Now we have a rank 90 theorem. We don't need the proof of this in this course, so I am not going to that. So T is from V to W. Okay. Rank T plus 90T equal to dimension of V. Okay.
Yes, sir.
Now if T is 1 to 1, we already know nullity is 0, right?
Yes, sir.
Okay, great. Now, this is domain, this is codomain, right? Domain is my V, codomain is W, right? Okay?
Yes.
If range, you know what is range? Set of all images,
Yes, sir.
right? Same definition as in function.
Yes.
So range of T is set of all images of T. Okay?
Yes.
If range is same as codomain, then T is onto. Same definition.
Okay, yes.
Okay. Now, in terms of dimension, what we can say? Dimension of range is equal to dimension of the codomain.
Yes, sir. Yes, yes, yes.
Dimension of codomain. Now, what is dimension of range? That is rank.
Yeah.
This is rank of T. If rank of T is same as dimension of the codomain, then you can say T is on. Okay? Clear?
Yes.
So this is all the thing you need to remember.
Hey, this particular link was one which was missing for me, like in terms of rank, nullity, rank, and the onto one. That was
Now this is clear?
always. Yeah, now it's clear, sir. This is the one which I was having constant confusion. I think. Yes, sir.
Okay. Okay.
Sir, when it is from R3 to R3, like we discussed about R4 to R3 or R3 to R4, it is happening. Yes.
What is happening here?
How to check for 1 to 1 and 1 to 1.
Huh. So again, the same thing. You have to check the nullity of T, and basically, if nullity of T is 0, then what happened in this case? I mean, if T is 1 to 1, suppose I have a relation when T is 1 to 1. Okay. The nullity of T is 0, right? Then
Yes, sir. Yes.
rank is dimension of V, that means dimension of R3, that is 3. Right? From the N90 theorem? Till this point it is clear?
Yes, sir.
Yes, sir.
Now rank is 3 means what? Rank is T is 3 means what? It is same as dimension of the codomain.
Yes.
Because codomain is also dimension 3. Because it is R3 from R3. Right? So what does it mean?
Isomorph.
T is on to, right? So if T is on to 1, in this case, when I am going to same dimension to same dimension,
Yes.
okay, so I mean vector space of same dimension, I map between those two. If T is on to 1, then T must be on. That means T is an isomorphism. Clear?
Yes. Sir, is it
Again,
possible?
conversely, if T is on to, then what? The rank of T is 3, right?
Yes.
Then nullity of T is 0, right? From rank identity theorem.
Yes.
That means T must be 1 to 1. So if T is on to, then T must be 1 to 1. If T is 1 to 1, then T must be on to. So if T happens to be either 1 to 1 or on to, then T must be an isomorphism in this case. Okay?
Okay.
Clear, no?
Yes, sir.
But sir, even two elements can be mapped to the same element in codomain, right? So in that case, it is also onto, but not 1 to 1, right? Like for example, in R3 to R3.
R3 to R3. No, R3 to R3 it cannot happen. R3 to R3, if it is on to, then it must be 1 to 1. If it is 1 to 1, then it must be on to. No other way. Okay? If two elements is mapping to one element, then it is not 1 to 1, no?
Yeah, it is not 1 to 1, but it is on to.
Then it cannot be on to also in R3 to R3.
Okay.
Okay? That is what rank 9 theorem is saying. Okay?
Sir, can you please go to that transformation where you have given the basis, you have given the image of the basis and transformed it. Please scroll up, sir, please.
Okay. This one, right?
Sir, yes, sir. Suppose we choose a different basis for the domain. Suppose we choose a different basis for the domain. Then we'll get a different matrix.
Yeah.
So that matrix will also have the same null space as that of the transformation. Is that what you mean to say?
When?
Not this one, sir. Go down, sir.
This one?
Yes, sir, this one. Suppose you choose a different basis for the domain. You choose a different basis for the domain. Then you will get a different matrix here. So the nullity of this matrix will also be 1.
Same. Yeah, exactly.
Okay.
Yeah,
Right,
because that only depends on the linear transformation.
Okay.
The null space may be different, whatever, but the nullity will be same. Because that
nullity
is only
will be
dependent
same. So suppose we want the null space of this different matrix and we want to find the null space of the transformation now. If you know the null space of this matrix and we want to find the null space of the transformation, then how do we go about it, sir? If you have the null space of the matrix, how we will find the null space of the transformation?
That will be a null space of this transformation. Null space will also be the same.
Okay. Don't we have to multiply the
I
null
don't know
space
where you have seen this multiplication thing. I am not getting properly where you have seen this.
Actually, the multiplication is for the vector from domain to 9.
Suppose we have the basis. Suppose the basis of this matrix is 1, 1, 1. Basis of the null space of this matrix is 1, 1, 1. Don't we have to multiply 1, 1, 0, 1 plus 1, 0, 1, 1 plus 1, 1, 1, 0 to get the null space of the transformation? In this case,
say it again.
The null space of this matrix is 1, 1, 1.
That is one vector just.
Yes, it's a basis for the null space of this
Null space
matrix.
1, 1, 1, right? Okay.
Yes.
That is
Now
what we got
suppose
here.
we multiply this each of these 1, 1, 1 with 1, 0, 1, 0, 1, 1 and 1, 1, 0. So 1 into 1, 0, 1 plus 1 into 0, 1, 1 plus 1 into 1, 1, 0. That will give the basis of the null space of the transformation. That's what I mean to say.
No, it's not.
Okay.
I really don't know from where are you asking this? You are saying,
Uh,
so see,
what I mean to say is that the
one
null
minute,
space
one
of
minute, one
this.
minute. This is the basis of the null space, right?
Yes, yes.
So why are you multiply each one of this with this one? What does it give anyway? I mean, is it supposed
Because
to give anything?
we have we because the this 1, 0, 1, 0, 1, 1 and 1, 1, 0 are defining the domain of the transformation. So
Right.
the null space of the matrix, the basis of the null space of the
This is
matrix.
the null space of the basis of the matrix.
Yes, 1, 1, 1. So
Mm-hmm.
that 1, 1, 1, each of
Mm-hmm.
we have to multiply with this in order to get the basis of the null space of the
This is the basis of the
transformation
null space
of the transformation.
of the transformation also.
Okay, okay, okay. So it does not depend on the basis which we take or basis which we take for the domain. Suppose we take a different basis for the domain.
Yeah, I mean, how does it matter?
Okay.
Sir, here I have a question.
See, I am giving you a simpler example. Let's see whether your doubt is clarified from there or not. Okay. So suppose I have a mapping from R2 to R2. Okay. Let's come to smaller dimension, R2 to R2.
Yes.
Okay. I am giving you this linear transformation. Okay.
Yes.
Yeah. Can you tell me what is suppose okay, so let's start with the basis of R2 for the domain. Let's take 0, 1, not say 0, 1, say 1, 0 and 1, 1.
Okay.
Okay. This is a basis for R2.
Yes.
Okay. Okay. So can now on that side codomain I have standard order basis.
Yes.
Let's not complicate there. Okay.
Yes.
What is the matrix of this linear transformation with respect to these two bases? This is beta and this is gamma. What is T beta gamma?
Oh, I think 1, 1.
So T of 1, 0 is 1, 0.
1, 0, 1, 0
And
and
T
T
of
of
1, 1 is
is also 1, 0.
1, 0. So it is
1, 0.
sorry.
1, 1, 0.
Yes, yes. Yes, yes.
Right?
Yeah,
Yes,
0.
yes.
Now, what is the null space of this transformation?
1.
1.
1.
Null space, null space.
Null space of this transformation.
0, 1. 0, 1 is
XY such that T of XY is 0, 0, right?
So 0y. 0y.
Exactly. So it is 0,
Y.
Y.
Right?
Yeah.
Yes.
So what is the basis of this null space?
0, 1.
0, 1.
This is the basis of this null space, right?
Yes, yes.
This is the basis given here for R2.
Yes, yes.
Now, what you want to do here?
Now
Without
the null space of this.
I mean, this null space, the basis of this, we can find independent of whatever the basis we have taken here, right?
Now suppose we are given only the basis of the domain and the matrix we have given, and we have given the basis of the domain. then can we find the basis of the null space
I
of the
mean, we are not
transformation?
giving you this. We are not giving you the transformation.
No, no transformation is given. We
So
are
the
given
matrix.
only the matrix, and we are given the basis of the domain.
So that is the defined issue. That's what not what I was doing earlier also.
Okay.
That is what I am saying. When I am giving you a transformation, then we can
Okay.
find the null space directly from there. And that is the
Yes,
same
yes.
from this matrix, right?
That is clear, sir. That is clear.
That is
If you are
clear,
given
right?
the transformation, we can find the null space. That is clear.
Okay, that
But
is clear, right? Now
suppose we are
suppose
given.
we don't know what this is.
Yes, yes, yes.
Okay? Suppose we don't know what this is. We don't know all these things, but we know this basis, these are given, right?
Yes, yes, yes.
This is given, correct?
Yes, yes.
Now
Matrix is
from this,
given. Yes.
can't you find out the transformation?
Yes. From this, if we are given the basis of the codomain, then we can find the transformation.
But when you are given a matrix, it must be, I mean, both these bases must be given.
Yes,
Otherwise,
yes,
this is
yes.
not fixed.
Yes, 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 yes.
Okay. So whatever way you are given, it is the same thing.
Okay, okay.
If this is also given, then you can get back to here, right?
Okay, yes,
You know
yes.
how to get back, right?
Yes, yes, yes.
You have to
That is,
write any vector in terms of this first, 1 0 and
yes,
1 1, right? So
yes, yes,
C1 1 0 plus C2 1 1. Then you know what to do. You know these are the image of T of 1
yes,
0, right?
yes,
This is the
yes,
image of T of 0. And then you get back. You will get back to the same thing.
yes,
Then
yes,
calculate the linear null space. Same thing will happen.
yes,
Okay.
yes.
Maybe you are
Okay.
confused with this thing. I don't know.
Sir, I have a question here.
Yeah.
In the domain, if we take any point xy,
Hmm.
using the matrix
Hmm.
to get the image in the codomain,
Hmm.
we can directly multiply only if the basis is a standard order basis, or
No, if this is standard, we can multiply directly, but this is not standard. For the domain, this is not standard one. So we have to really find what is C1 and C2.
okay.
This is not standard, no?
Correct.
So
So,
this is C1 plus C2 and this is C2,
hmm,
right? So C2 will be Y
hmm,
and C1 will be what? C1 plus C2 is X, so X minus Y, right?
hmm, yeah.
Okay. So XY will be, so T of XY is X minus Y, T of 1 0 and C2 is Y, so Y T of 1 1. Okay, is it clear?
Yeah.
Now you know what is T of 1 0
Yes, yes.
from the, because the matrix was like this.
Hmm.
Okay. So these are in the column. So basically T of 1 0 is,
Plus 0 into 0, 1.
right. That's why you have
Yes,
written those in column.
yes,
So
yes,
this is 1 comma 0
yes,
and T of 0 1 is, sorry, T of 1 1. Again it is 1 comma 0.
1 comma 0.
yes,
So this is X minus Y 1 comma 0 Y 1 comma 0. So X, this is the transformation we got back, right?
Yes.
yes, yes.
So same thing, it doesn't matter. This is, that's why it is called representation. Okay.
Okay,
Whatever we have to calculate in terms of directly explicit definition of the transformation, we can do the same thing using matrices.
okay. Uh, okay, sir.
Okay. So any more doubt till linear transformation?
Yes, sir. Clear.
Hopefully it is clear, right? Linear
Yes,
transformation
sir.
basis.
Yes, sir.
So please upload it later, sir, to the email.
Huh?
Uh, please upload this later, sir, after the
Uh-huh,
session.
I will upload this. I will
Okay.
upload this.
Thank you.
So any more doubt till basis, linear independent, dependent, and linear transformation, nullity, rank, null space, range space. All these are clear?
Yes, sir.
Yes, sir. Yes, sir.
Okay, great. So in the next session, I think we will start with affine space and the rest of the part of week 8. Okay. Yeah, and inner product space is also remaining.
Sir, multivariable calculus, when do we start?
It will be in the last session. Multivariable calculus. Because already we
Okay.
have completed the multivariable calculus, right? Just recently.
Sir, can I ask a
Yeah.
doubt about multivariable calculus here?
Yeah,
You
go
said
ahead.
that the gradient vector is perpendicular to
Tangent plane.
the tangent plane.
Yeah.
So, sir, is there a proof for that? I tried a lot to find the proof, but I'm not getting any proof for that.
Proof of what?
Proof of, that the gradient vector is perpendicular to the tangent plane.
So you know how to find the equation of the tangent plane, right?
Yes, 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 yes.
And do you know how to prove in 3D when a line is a perpendicular to a plane? I don't
Yes,
think
you
it
have
is
to
discussed
the
in
scalar multiply it and it will be 0.
scale multiplied with what?
If
No,
you
no, it is
multiply the
no. That is perpendicular to a vector you are saying. So suppose this is a plane. Okay. You want to find out this. This is your vector. Suppose this is your tangent plane.
yes, yes.
Right?
So
This
any
is your
vector,
derivative.
okay, okay.
So this you have to prove this is 90 degree, right?
Yes,
I mean
yes,
it is
yes,
normal to that plane. And normal from any
yes,
direction, right?
yes, yes. So this plane is an affine subspace. You scale it down to the subspace that is containing 0, and then you take any vector on that subspace and you find the scalar multiplication of that gradient vector with the subspace that should be 0. That's what my approach was.
No, that is not the case. It is perpendicular to the tangent plane, but that does not say that any point on the plane, if you consider it as a vector, that vector is perpendicular to this norm. That is not it's what it's saying.
So suppose the tangent plane equation of the tangent plane is z is equal to
Hmm.
z is equal to
So
f
any plane, equation of any plane will be like x plus by plus cz
cz.
equal to d. Right?
Yes,
This is
yes,
the
yes,
general form of plane.
yes, yes, yes,
Okay.
yes.
Now there is a condition which involves direction cosine.
Hmm.
So in 3D geometry, there is
Hmm.
something called direction cosine. Using that direction cosine, you can find the equation of the line which is perpendicular to this plane. That is
Yes,
not
yes.
what we have discussed anywhere in this syllabus.
So my approach was that you take the plane ax plus by plus cz equal to 0. So that is
Okay.
a subspace. That is a subspace
Hmm. Hmm.
containing 0. Now
Hmm.
this gradient, if it is perpendicular to x plus by plus cz equal to d, then it should be also be perpendicular to x plus by plus cz equal to 0. It should
Okay.
also be
Then
perpendicular to x plus by plus cz equal to 0. So if you take any vector on ax plus by plus cz equal to 0 and scalar multiply it with the gradient vector,
so
then
it
that
is
value
that's
should
what I
be.
am not. That's what I am saying. It may not be perpendicular to any vector on the thing.
No, I'm not talking about any vector on the affine subspace, that is ax plus by plus cz equal to d. I am talking about a vector on ax plus by plus cz equal to 0. I'm talking
Okay.
about on that plane. So if you take
Okay.
any vector on that plane, that
Hmm.
that vector should be perpendicular to the gradient vector. That is what I'm
Okay,
saying.
so let's can you give me an example so that we can
So let us take a
We take
tangent plane
any
for
line.
z. Z is equal to fa. Z is equal to fa f uh, uh, f fab. Sorry, that is what the tangent plane is, right? Fab plus uh, f uh, fax of ab. Yes, yes, this is the plane, right? Y minus. Now you expand this and you take all the variables towards one side. So let us say
so
that
basically anyway the corresponding vector
x
subspace will be
x.
like this,
Yes, sir. Minus z is
right?
equal to 0. Yes, sir. Yes, sir.
Right.
Yes. So
Then
and a gradient vector is of the form fx ab comma fy ab. So the third option is not given. So gradient vector in 2D will be having only two fx and fy only. No, there will not be a third
so
one.
this is your vector, right? This is your function, right? Z equal to
Yes,
fxy. This is
yes.
your function, right? And what
So
is your
this we
gradient
have
vector?
to.
That has only these two dimensions. This is the gradient vector, right?
Yes, yes, yes,
Yeah. Now we want to show that this vector is perpendicular to this plane,
yes,
right?
yes, 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 sir.
So now what you are doing?
The any vector on this plane is of the form x y uh, is of the form
See, can you
x.
see the difficulty to doing that? Because this is a surface, right?
No,
And
sir.
this is
Any
only a
vector
vector of
on.
two dimension.
Yes, sir. How
Here, when you
that is what.
consider a point in this vector space, in this subspace, that is in 3D, three dimension. So how can you
Yes,
show
yes.
directly using the dot product? That's what I was telling earlier.
So, sir, how to
So,
prove
sir,
that
you
this
need to,
gradient vector is how
That's
to
what I am
prove this?
saying. You
you
cannot
need to
show
take
directly
2
from
points.
inner product. Yeah.
Okay. So, sir,
What?
suppose any vector on this plane is of the form x y comma x y comma fx ab x, any point on this plane, if the plane which you have written here is of the form x comma y comma fx ab plus fy ab, fx abx plus fy abx. So yes, sir, please take up any point on this
I got
plane.
it. Then
So that will be a vector of this plane, right? Now,
right.
if you multiply this with this gradient vector, you will get the
How can you
first
do
two.
multiplication directly? That's my point. This is in R2.
Yes, this is an R2. But suppose we take the third as minus one, then
Why?
the
Why
third
you will
one
take third one as minus one?
in the illustrations which you have shown us in the previous class, in both the illustrations, the third vector of the gradient vector is taken as minus 1. So that is why I,
Because
because
that's one is correlating with this tangent plane. That's why it
yes,
was
sir.
taken.
Okay, okay.
Okay. Here from here this minus one was coming.
Yes, 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 yes.
Okay. So these basically if you have the x, this what I have written here, then I can write suppose d is non-zero. Okay.
Okay.
I can express it like this. Okay.
Yes.
Okay.
Okay,
Then
okay.
this and this. These are basically the direction cosine of that vector which is perpendicular to this plane.
This concept of direction cosine is not there in the
Not there in
lectures.
this levels, yeah. Because this is purely in 3D geometry. We don't need that here.
Okay, okay,
Here
okay.
gradient vector, what I have mentioned earlier also in the previous slide session, the gradient vector is defined to be the normal which is perpendicular to the tangent plane. That is the
But if
definition of
sir
the
the
gradient.
gradient vector has only two components, how can we say that it is perpendicular to this plane? How can there is no way to prove it, or the proof is not in this, like in this?
I mean, what does that mean? Suppose you have xy plane. Okay?
Yes.
This is your xy plane, right? Here
Yes.
somewhere this is your y-axis, this is your x-axis. Okay. Now can't I say 1 comma 0 is perpendicular to this plane? Sorry, not 1 comma 0. This perpendicular direction to this z axis. Can't I say
Yes.
that this is
Yes.
perpendicular to this xy plane?
Yes. Yes. Yes.
This
You
is
can
the
say that.
yeah, yeah. Okay.
Okay.
So, sir,
So
what
here
is
what we are doing here, basically when I am talking about a function of two variable, I am taking the images along this z axis. Okay.
Okay.
This is my, so whatever the surface I am getting here, this is z equal to x fxy, right? So I am
Yes.
taking
Yes.
a
Yes.
point in xy and taking the images here. So that's why I am getting this surface, right? So basically I am
Yes.
writing fxy minus z equal to 0. This equation, right?
Yes. Yes.
This is what I am plotting here. Okay.
Yes.
Now
Yes.
I am getting a tangent plane to this. So this is also depending on x, y, and z. Okay. So I
Yes.
am
Yes.
getting a tangent plane, but both of them has dimension 2.
Yes.
Okay.
Yes.
Because tangent plane is basically an affine plane, we know it is of dimension 2.
Yes.
Okay.
Yes.
And then I am considering my gradient vector for f, x, y alone. Okay. That's
Yes.
why
Yes.
it is of dimension 2. It is perpendicular to this. Is it
So
clear?
how can it be perpendicular to this three-dimensional plane, sir, in that case?
The plane has dimension 2.
Okay.
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 I mean, this is just a direction vector we are taking here in R2. I am saying the
Okay.
gradient vector denotes the direction in which the perpendicular of this to this plane is basically situated.
Okay.
Okay, is it clear?
Sir, it is, I'm not able to,
No, sir.
uh,
Not clear.
no, no,
Yes,
sir.
sir. Because in previous illustration you saw gradient. It was in a 3D. So I think for 3D we have to three
Ah,
coordinate.
so, yeah, yeah. Okay, let me. So, okay, which one?
So what does it mean that if we say that gradient vector is perpendicular to the plane where we want to take at some specific point? So does that mean that in perpendicular to the plane there is no rate of change? M- Means what is the significance of saying it is
1
perpendicular?
minute, 1 minute, 1 minute. So let me see what I have sent you.
GeoGebra links, yes, sir. Some links of GeoGebra.
This is not. I think this is the earlier. This is the earlier one, right? This is
Yes,
not
yes,
that.
yes.
I think it's third one.
No, these are
No,
the
no.
previous ones. Yes.
This is previous one. Okay, I can find it here itself. Do you remember the date?
Date, I think On Friday, I think. No, not on Friday. Friday, I think it was Friday.
It was posted in the portal.
Yes,
The
yes,
links.
yes, yes. Yes, the links were there in the portal.
So it should be here. No?
It's on
Maybe
the
this one.
Tuesday, sir. Tuesday, 22nd.
This one is not.
I think the links came
22nd.
in the email. I think the links came in the email.
Maybe that is the case. Okay. 22nd, right? This one. Gradient to this one.
Yes, yes, this one, yes.
Yeah.
Yes,
Yeah.
this gradient vector, how it is perpendicular. Because every time the tangent plane will change, the gradient vector should also change in order to become perpendicular.
Right, right.
So
That is
if the
changing,
gradient
no?
vector, if the gradient vector is having only two variable, is having only two components, how can it change every time? How can it change in 3D every time the tangent plane changes?
Because I think that there is the third corner is taking as 0.
No,
Not
no.
0, they have taken it as -1. They have
One
taken
minute.
it as -1.
Yeah, so, okay. So, first of all, what is tangent plane? Let us understand that. What is tangent plane at a point? What does it mean?
Uh, it
Plane
is a
created
plane
by
of all tangent
all
lines.
tangents. Yes.
All tangent line passing through that point, right?
Yes,
Yes.
yes, yes.
And this line, what we are showing here, this line means what? This line is perpendicular to all those tangent lines, right?
Yes, 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 yes.
This line is perpendicular to all those tangent line, which is passing through
Yes,
that
yes.
point itself, right? That
Yes,
is the
yes.
normal direction to the tangent plane, okay?
Yes, yes.
Yeah. Now I am saying the plane has some inclination along this xy plane, right?
Yes, yes.
So if I take this, if I take this one, this equation, this is the equation of the tangent plane, right? So let me write
Yes, yes.
freshly somewhere. Fx x a comma b x minus a x minus y minus b equal to z minus f of a comma b, right?
Yes, yes, yes.
So if I am writing this as ab x ab y
Yes.
minus z,
Minus Z.
if I take it on both sides, the fx a comma b a plus b, some constant basically, right?
Yes, yes,
So
yes.
this is ax plus by plus cz. So c is here -1. So
C is
let me write
-1.
this and some constant d, right?
Yes.
This a is your fx a comma b
Hmm.
and b is your fy a comma b,
Yes,
right?
sir. Yes, sir.
And if you write this a comma b as the vector, this is your
Yes.
gradient, right? At that point,
Yes, this is a gradient. Yes, yes.
this is your gradient, correct?
Yes, yes, yes.
So now the equation of the line which is perpendicular to the plane. Suppose I have plane ax plus by plus cz equal to d. Okay.
Hmm.
Do you know what is the equation of the line perpendicular to the plane? Anyone who have studied 3D geometry?
I found it using the by making it an affine space. I tried to find it.
No, I am not asking that. I am asking
Okay.
equation of the line perpendicular to a plane.
No, sir. That I have not studied 3D geometry, so I don't know.
Anyone?
Slope of m1, m2 will be -1. That
No, not directly. Probably.
But that way also you can find, na, sir, by making it an affine subspace,
So what
the
is
vectors will be perpendicular to that by making it a subspace containing
so
zero. If you
what is
make
the
it,
small a and small b? First of all?
Yeah.
Small a, small b here. What is it? Small a and small b.
it's the
That
point
is
at
that is
which
the
the
point at which we are
Okay.
calculating this.
Oh.
so that approach is also right, na, sir, by making this a subspace that is equating d to zero, that is a subspace. That vector should also be perpendicular. This whatever vector we are talking about, it should also be perpendicular to that plane. If you can take d equal to zero, that is the subspace of this. It should be perpendicular to that also, no?
Yeah. So if you look at this picture, can you point out where the gradient vector is actually? This is a line, right? This is not a
Yes,
vector.
yes,
This is a line,
yes,
right? So what is
yes.
your gradient vector here?
Slope of
Gradient vector.
line.
You basically what you are doing, you are basically transforming this plane to the origin, okay?
Yes,
And you
yes,
are
yes,
shifting
yes,
this line to this origin and getting this vector, right?
yes, yes, yes.
So if you have to shift this to our origin also, right?
Yes, yes, yes. Yes, we have to shift it to
So
the origin.
to the origin also, right? Then those
Yes,
two vectors are perpendicular to each other,
yes, yes, yes.
correct?
Yes, sir.
So have you shifted this line to origin? That you have not done, right?
Yes, sir.
Because that's why I'm saying. So first of all, you have to find the equation of this line, which involves this 3D geometry. What I was saying, that reaction cosine. So you have to find the equation of the line. Then you have to pull down this line to origin.
Okay,
Okay.
okay.
Then you get what is the vector you get remaining, something comma zero. That first two coordinate will be your gradient vector.
Okay, okay, okay.
Okay.
First two coordinates are anyway the gradient vector. The question is about the third coordinate. The third coordinate
Why
is
first two coordinate anyway? I mean, is this so clear?
because the gradient vector is if you take the gradient vector and multiply it with, and you take the third one as -1, then you get the proper multiplication. In Please go to the notes part, sir. If you take a gradient vector is fxab comma fyab, and you take the third vector as -1, then if you take the multiplication of this, uh, then you get zero. Then you get zero. That's what. Hello.
Yeah. Go ahead.
So so I meant to say that if you take a point on this plane, so A is that point is of the form x, y, comma minus ax plus by, ax plus by, x, y, comma ax plus by.
So
And if you
see
take the
this.
perpend,
Go
yes,
ahead.
yes, sir.
Yeah, you finish first, then I will tell.
And the vector which is perpendicular to this plane, which is x, y, ax plus by, is exactly uh, uh, a b comma uh, -1, a b comma -1.
Okay.
So can you write it down, sir?
Yeah, tell me.
The point corresponding to this d equal to 0, suppose we take d equal to 0, then the point on this plane, which is the subspace, is, and if we consider c as -1,
-1.
if we
Yeah.
then the point on this plane is
And
x,
there are infinitely many points. Yeah.
but if your general point is x, comma y, comma y, comma ax plus b, by, yes. And this is a vector on this plane. This is any vector also on
Any
this
vector on
plane.
this plane, right?
Yes.
Exactly.
Now if you multiply it with vector which is a comma b, minus 1,
That
minus
will
1,
what you'll give.
that you will get 0. You will get 0.
So these two are perpendicular to each other, right? That's what you are saying.
Yes, 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 yes.
So what is the problem there? I am not
So
getting
how
it.
this minus 1 came? How this minus 1 came? Because these two AB are clear that they are the gradient. They are forming the gradient. How come this minus 1 came?
So yeah. So basically this now. So okay. Now let me tell what is going on behind this. So suppose this is the equation of a general plane. Okay. Now any
Yes.
line which is perpendicular to this plane, any line which is perpendicular to this plane, and passing through this, suppose a comma b comma f of a b, right? That is what we are doing here. Now any line which is perpendicular to this plane is basically x minus a by a. This is the equation line in 3D. Okay.
Okay.
Yes, sir. Y minus Z minus F
AB by
upon C.
C. Okay. This is the equation of the line in 3D. And in this line,
Okay.
what you are seeing in this picture is basically this straight line.
Okay.
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 That portion is clear. And these are called basically the direction cosines, which I was telling earlier. Right?
Okay. Okay.
Okay.
So
So this is the line which is perpendicular to this plane.
okay.
Okay. So basically what you are doing now, you are pulling down this plane to a plane which is passing through origin. Right?
Yes, sir. Yes, sir.
So you have to pull down this one also passing through origin.
Yes, sir.
Right?
Yes, sir.
Okay. So what is the direction cosines you will get? A, B, and here what will be? Minus 1, right?
Okay.
Your C is minus 1, right? That is what you
Yes.
are doing. And
Okay.
this is basically your gradient vector.
But directional cosine concept, I don't know, sir.
Has not come, yeah, exactly. But that's what
because
I did not want to go here. But okay.
Okay.
Now, at least you get an idea, right?
Yes, sir. Yes,
Suppose
sir.
you have a plane x, y, so this one, this is the equation of a plane. Then this is the straight line which is passing through that point a comma b comma f of a comma b,
Yes,
and
sir.
perpendicular to the plane. Okay.
Yes, sir. Okay, sir.
And here in this case, our tangent plane, this is the equation of the tangent plane, right?
Yes, sir.
I mean, not this one. It is here something if some constant will be there. Basically,
Yes, sir.
so this a b and here it is minus 1, right?
Yes,
So
sir.
this is
Yes.
the vector which is basically perpendicular to the any vector on the plane.
But is this the gradient vector, sir? A B minus 1. Is this the gradient vector?
No. Gradient vector is only a comma b for z
But
equal to x, y.
we are claiming that the gradient vector is perpendicular to the plane.
I mean, not exactly the gradient vector. That is the issue. The direction of the
Actually,
gradient.
this line is not gradient. It's another line. Yes, sir.
What?
Sir, this line is not gradient.
This line is not gradient vector. That is my point. This line is not gradient vector. The direction cosine is of this line involves the gradient vector.
Yes, sir. That was
So
confusing.
the tangent plane with gradient vector was written. So I thought that this black line is the gradient vector.
Yes,
And
how
I
a
was
line can be a gradient vector? No.
okay.
Vector is a point, right?
Yes, sir.
So how a line can be a gradient vector?
Okay.
Okay.
So line cannot be gradient vector.
Yeah.
But it is in the okay. Right.
Yes, sir. Now it's clear. Okay.
Yeah, no?
Yes, sir.
Okay. So anyway, I mean, too much 3D geometry you don't need anyway. But as you asked, I have told you. But if some of you don't understand this, no issue at all. Okay.
Okay.
You basically you want to remember is basically the gradient vector, the direction of the gradient vector. So in R2, this is in R2, right?
Yes, that is clear.
A comma
yes,
B.
that is clear.
So this is here. Suppose this is xy plane. Here I have z axis. So in R2, This is the gradient vector, right?
Gradient vector. Yes, yes,
And
yes.
here is
That
the
is
line.
clear.
Here is the tangent line.
Yes.
I mean the line which is perpendicular to the tangent plane.
Yes,
Okay?
sir.
So these two are in the same direction.
Yes, sir.
Okay? This is A comma B. Okay?
Yes, sir.
This is on R2, right? So A comma B comma 0 you can take if you want.
This will be
Right?
in the XY plane. This will be in the
This will be
XY
in the
plane.
XY plane. That's why it is
Yes,
a
sir.
2 coordinate.
Yes, sir.
Okay? The gradient vector. If
And
you
this
want to
line
see it
will.
as a vector, the
Yes,
line
sir.
will be on somewhere upstairs. No?
Okay.
Depending on the point where how the curve look like. But the direction of that line
Will be the same as
away
the
from the
direction.
plane, away from the plane. That direction is on the same direction of the gradient vector.
Okay, okay.
Okay?
Okay.
Yeah.
Yes, sir.
Okay. I think it's more or less done. So yeah. Okay. So let me stop the session here and we'll start again in the next session. Okay.
Okay. Thank you,
Okay.
sir.
Thank you, sir.
Yeah.
Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.